Okay, so continuing from what Rob kind of introduced, so hopefully everyone has some understanding of what Bohemian eigenvalues are. I did a lot of work on actually computing Bohemian eigenvalues. As Rob mentioned, I've probably computed over 1 trillion, the eigenvalues of over 1 trillion low-dimension matrices. Before I jump into my talk, since Rob didn't quite make it to the website, this is bohemianeigenvalues.com. If you're interested, I maintain the website. It has a few definitions on here, has our contact information. I am also working in the Orca Lab, the Ontario Research Centre for Computer Algebra, as well as a few other people here. So there's a link there to our research group. The gallery, so this is what Rob mentioned. Just a ton of fun images on here, some of the Mandelbrot ones here. All sorts of other stuff. The one from the shirt is this one here. So if you're interested in that, there's a little description there of exactly what that image is. That's actually the exact image you see on the shirt. And all sorts of other things. Circulant one, which Rob showed on the Riemann spheres there, just on the plane. This was generated by an undergrad student a few years ago. All sorts of other fun things. So I'll kind of go through what some of these are and how I actually went about generating these images and really where this project started from for myself. And this image here, so that's somewhere in the Czech Republic, so that's in Bohemia. Stole that from Google at some point. So I think so the project at my end started about 5 years ago, I think. Rob was teaching an experimental math course. And he kind of proposed that I do this project where I explore the distributions of eigenvalues of random structured matrices. So I went back to my actual original project proposal from this course and pulled a few points from that. So I was originally going to look at kind of the eigenstructures, so the distributions of the eigenvalues, the pseudospectra, which I never really got to, and the eigenvalue condition numbers, and how those are distributed across these structured random matrices. And a few definitions. So before the term Bohemian came to be, the term Bohemian, I think that was just a random text from Rob at about midnight one day, saying, hey, this sounds like a really good name. So BHIME for bounded height integer matrix eigenvalues, that is what I originally referred to them as. This acronym will appear here and there from kind of the pre-Bohemian days. And when we refer to a family of Bohemian matrices, this is kind of some defined set of matrices where the entries are integers from a finite distribution. And so Rob gave a few examples of those. I'll give some more examples. Bohemian eigenvalues, just the eigenvalues of those matrices. Eigenvalue exclusion zones, so again, Rob kind of mentioned that. These are those holes that you see in these images. So we are interested in understanding why those appear, what are their dimensions. Typically, there's an eigenvalue right at the middle of them. So typically, you'll get kind of this eigenvalue exclusion zone around 0 in the complex plane, and then very high density at 0. And rhapsody, which is kind of when the inverse is also Bohemian. So back when I started this, obviously I needed to write some code. I was using Matlab at the time to actually generate these images. So Rob was really excited about all these different matrix structures, and I was kind of, okay, take a step back. I just need a really simple test example to start this project with. So I picked, 5 by 5 matrices. They're small. Probably not going to be too interesting. They're just 5 by 5. Entries -1, 0, 1. Again, small set. Doubt it'll be interesting, but it's good to start with. And as Rob mentioned, so there's about 847 billion matrices in this family. So during the course, I created this image. This was one of the first Bohemian eigenvalue, if not kind of the very first that I actually created. This is a sample of, so I have some details on the next slide, but this actually came from kind of my final project in that course. This is not all 847 billion here. This is a random sample of, I believe, 3 billion. And that's because at the time, I was not able to do all 847 billion. In the second part of my talk, I'll discuss how I did that. There's a lot of matrices to compute the eigenvalues of. And I took kind of a different approach to do that versus how I typically generate these images. So that first image is a random sample of 3 billion matrices. I just did this on a laptop a few years ago. I let it run for about 60 hours, so this took a long time. My Matlab code was not as optimized at the time as it is now, so you could actually do that a little bit faster now using kind of the MATLAB code that I have available, and I'll go through in a little bit. It took 380 gigs of just storage space. I think I had an external hard drive plugged into my computer that I was just offloading all these .mat files to, containing all the eigenvalues. Again, there's been some improvements there in terms of actually storing these things. And given that, if we wanted to actually do the full set of matrices, we'd be looking at close to a year to actually do the full computation. 50 terabytes of storage. I don't have access to 50 terabytes of storage. So to do this computation numerically, it's just kind of infeasible. It's no point wasting a year trying to compute all these things. There are better approaches. So just really simple to start. If you want to compute Bohemian eigenvalues, you can do it in 11 lines of MATLAB code. And if you actually run that code, I'll run through it in a second, but if you run that, you get this out. I don't know how good the contrast is there. But you do actually see that same structure. So that's a random sample of 1 million matrices. So this is the 5 by 5 example again. There's not a whole lot to actually get started with this. So the actual code here, just kind of running through it. It's really nothing all that fancy, but start off with L for lambda, which is just a 5 by 1 million matrix. That's going to store the eigenvalues. Then you just loop through 1 to 1 million. The randi function will generate a random integer matrix with integers from -1 to 1. Compute the eigenvalues of them, throw them into a column of L. The reshape then just takes this matrix and converts it to a vector. And then the hist3 function will just actually create a two-dimensional histogram. I don't know why it's actually called hist3. It'll create a two-dimensional histogram, in this case separating out the imaginary and real parts. And then image SC, that will actually do the heat map. I take the log. I think I always take the log when I actually create these. 0 is always just completely off the scale in terms of density, so is the real axis. So that kind of normalizes things down a bit. So this takes less than 10 seconds to run. It's kind of crazy that you can compute 1 million eigenvalues in under 10 seconds. I'll have a little more details on that in a second. As you can see, so the real axis is very, very high density. This is a normal kind of feature of these images. And then the complex eigenvalues are much lower density. If you prefer Python, you can do it in Python. So this is just same thing, just converting the code from MATLAB to Python. Creates pretty much the same image, actually a little nicer looking. So again, that takes less than a minute to actually make that. If you prefer Julia, again, kind of same code there, 13 lines long. And that'll actually produce pretty much the same image as Python, because I was using pyplot there when I made that image. When I was making these slides, so I kind of noticed when I was running these various examples, Julia seemed really fast to do this computation, and Python seemed really, really slow. It's a little bit of a divergence. I use Matlab mainly for all of the work that I do, but I was interested, so I'm kind of moving out of academia right now as I complete my PhD, which means in a year from now, I'm not going to have access to Matlab. So I need some way of doing these. I'm not going to just abandon this project, even if I'm out of academia. I need some way of actually being able to generate these images, but I'm not going to have Matlab. So I was trying to determine what language should I use. I have Julia, I have Python. Python has kind of the user-friendly advantage. Everybody loves Python. But Julia was absolutely ridiculously fast for this. So to give some idea, Julia took about 5.5 seconds on average, or not on average, that was the fastest, to compute the eigenvalues of 1 million random 5 by 5 matrices with -1, 0, 1. MATLAB's up at about 6.7. And then Python, using NumPy, so the numpy.linalg.eigvals function, it's closer to 30 seconds, which was a little disappointing. Because I was really hoping to use Python to actually kind of generate maybe a Python package for generating these images to make it a little bit more accessible to those people who don't have Matlab available to them. So I looked into this a little bit, found a Stack Overflow post where somebody was talking about why is Python so slow, or why is NumPy so slow at computing eigenvalues. That pointed me in the direction of Intel's MKL library, which is their math kernel library, something like that, which has optimized functions. You don't have to interact with it anyway. It's available as just an Anaconda package, which you can download and install, and supposedly that should improve performance. I tried it yesterday, didn't really see any gains. I'm going to keep working with it. I'm hoping, I know a friend of mine had a lot of success using the Intel MKL libraries to really gain performance in some of these things. But I'm going to keep working with that and hoping to get that number down to kind of a comparable range to those. I don't see otherwise why it would be kind of five times slower. Hoping I can use Python in the future. One other thing, so the second column here, that's actually the time to generate a million 5x5 matrices on average. Python again was slow. The function I used in Python, so I used, go back to it. So I used the np.random.randin function, so -1 to 1. If you use np.random.choose, which will randomly choose from a set, that actually takes about 10 seconds on average. So even how you generate these matrices can have a very large impact on how long it takes to actually compute these sets of eigenvalues. Okay, so back when I was actually first working with this, is kind of looking for what does this tool, or what does this set of functions that I want to develop, what features do I want that to have? So one of those things was ease of use. I want this to be accessible. I want other people to be able to really easily generate these images, have fun with it, just very little overhead in terms of getting started. Flexible. Rob has a tendency to just give me new classes of eigenvalues, like, hey, I'm in New Zealand, but I need this doubly companion image for tomorrow for a talk, which is now on your shirt. This has happened many times.
He did it.
This has happened more than a handful of times where I've got those messages. So I can really easily just write a single function that will spit out a random doubly companion matrix, plug that into the code, and 5 minutes later have an image. Send it off to Rob in New Zealand. I think I actually put that one on the website. It needs to be fast. So in the previous slide, you saw this stuff is pretty fast. If I'm generating these images, I don't want to sit around for 10 minutes just to see one image. I spend time just kind of quickly firing through these things. There are cases where I will generate very large numbers of these. So I might generate 1,000 or 10,000 different images coming from different classes. They're not Bohemian. I'll mention them in a minute. So the ability to do that has its advantages. Visually appealing images. So that comes from a mathematical point of view as well. So these are always colored by density, or almost always colored by density. You want to be able to look at the image and have an understanding of where is the high density regions, where is the low density regions, something that you can visually look at and understand what you're seeing, and kind of make conclusions from that. Numerical accuracy, so whatever we're using to compute eigenvalues, it better be computing eigenvalues. There are cases where there is numerical error. We can't do anything about that. But we don't want to use some horrible approximation for computing eigenvalues that just destroys everything. In terms of the features that this has, so I will give a little demo of kind of the Matlab code I have. This gets into the flexibility and ease of use kind of stuff. So access limits for your actual images. The ability to actually create images that use more eigenvalues than you have memory on your computer. So I did that 3 billion eigenvalues case. I don't have, I think I said 340 gigs of RAM, or 340 gigs of storage. I don't have that much RAM on my laptop. To run it in parallel, so MATLAB has some really nice parallel tools. Take a for loop, change for to par4, and you have a parallel loop. And they have some documentation on how to actually optimize that code, which is really nice. This option, so ignoring real eigenvalues, I noticed that the real axis almost always has very, very high density. So sometimes that will kind of hide the information in the complex eigenvalues, just because of how the coloring works. So there is the ability to actually just throw out all real eigenvalues in some of these images. So sometimes you'll see one where you're like, where's the real axis? It might have been excluded for that reason. There are symmetries across the real and imaginary axes in a lot of these actual images that we look at, which are inherent in the problem. So if you have a real matrix, it's going to have that symmetry across the real axis. And then so kind of just the ability to use custom color maps, whether it's the default ones in MATLAB or whether you just want to generate your own. So the whole process is kind of broken down into 3 steps. And those little snippets of 11 lines of code are actually kind of broken down into this similar 3 steps. First step is compute your eigenvalues and save them somewhere. So this is the most computationally intensive part. If you want to compute 3 billion eigenvalues, you can do this. You can do it in chunks of a million. You can do it in chunks of 10 million. For this part, I'll get into details in a second. The second part is then read in all that data and generate this 2-dimensional histogram over the complex plane. And then the third part is actually spit out a plot. Third part's the easiest. So in terms of computing the eigenvalues, so I added the ability to really chunk the computation into maybe do 1 million matrices at a time and then offload that to a file, do another million, offload that to a file. This allows you the ability to do maybe 1 million matrices, see what the image looks like, maybe there's some detail missing there that you want to see. So then, I don't know, do another 10 million and then you don't have to recompute that first million. Maybe you want more, so you can crank it up to 100 million. You can just keep adding to that. The actual eigenvalues, there is an option for this. By default, they're stored in single precision. We're not really looking at these typically at a scale that where it would really matter. If you need double precision storage for those, you can. There's an option that allows it. And then this whole computation can be run in parallel. Again, that's just kind of really easy to do in MATLAB. Nothing you have to think about. The second step, so this is where that hist3 or that numpy.hist2 2D maybe function comes in. So you have to read in all of these eigenvalues. You can't read them all in at once, but you can read them in file by file. And then just store them into a 2-dimensional histogram. This is where you can actually specify the limits of your histograms. This is the axis limits of your images. This is also where real eigenvalues are discarded. There is a tolerance parameter for that as well in terms of what is a real eigenvalue. You can also throw symmetry onto this across the real and imaginary axes. One thing that's not mentioned on here, there is actually an option to map the eigenvalues with a function. So sometimes we see this inverse symmetry, so this 1 over z symmetry. So you can actually create the image of just the eigenvalues, and then you can also do 1 over the eigenvalues and create that image as well. I don't use that often, but sometimes this can be useful. This can also be done in parallel. Again, there's some nice tools. So in MATLAB, you can have a single array, then you can go over a par for loop and fill in that array however you like, and MATLAB takes care of the overhead there, which is really nice. The plotting part, there's not much to it. You just take that 2D histogram and plot it, apply a color map, and then make the background whatever color you like. I'll go into a quick demo, so I'll leave that up for a second. GitHub.com/Bohemian Eigenvalues. So this is our kind of GitHub user account. There's not a lot on it right now. Hoping to add more stuff in the future. So any papers that we publish, we're hoping to have a repository there with all the code needed to reproduce kind of results in those papers. That's one thing I'm hoping to work on actually at the workshop, is organizing some work that we had before into their own repositories there. So this BHIME project one, this is the MATLAB code that I've been developing over time that I've used to create all these images you've seen. If you open that up. So that'll take you to GitHub. And then, depending on your familiarity with Git, the big green button, you can either download it as a zip or clone it with Git. I'll just give a quick overview of what's actually in there. Hopefully everyone can see that. Just gonna go to this view. Okay, so there's a few folders in there. I'll quickly mention, so the data and maple folders for generating these images, you don't need those folders at all. The data folder though, so this is what contains, so when Rob mentioned he was using all those 1.8 million polynomials for the degree 5 -101 case, This charpoly's 5x5 d3.txt file contains all of those, as well as kind of how often they occur, as well as a 4x4 and 3x3 and so on case. So if you're interested in analyzing those polynomials at all, they are available on Git. Another thing I'm hoping to accomplish in this workshop is actually get a few more classes of matrices up there, so the -1, 1, as well as a 0, 1, all the way up to 6x6. So I'll have those on there soon if you're interested in looking at them. The Maple folder, so this just has a few functions. So is it read polydata.mpl, that's a Maple function that will actually read in those text files. There's a few other things that I use on occasion there. Make poly square free is just kind of a wrapper around the square free function in Maple, just that is useful sometimes. They all have documentation in them if you actually look at the files. If you're interested, you can talk to me. And in terms of the actual code for creating these images, actually let me go to Matlab. A little easier. One thing Matlab needs to fix is when you plug in a new monitor, it always freezes. This problem has been around for at least a year, although I have not filed a bug report. So if you find bugs in my Matlab code, please let me know.
Mention the hide bug.
I will. I have a slide. All right, so let me just close that. Okay, so once you have this Bohemian folder, so the whole SRC, that whole folder, you just have to add that and all the subfolders to your Matlab path. Within there, it's kind of broken down into those 3 steps I mentioned before. So data generation, that's step 1, that's computing your eigenvalues. Data processing, that's generating the 2D histogram. And then image processing, that's actually creating the image. You don't have to worry about what's in those folders, you just have to use what's actually in those. And I'll get it to an example in a minute. There's not much you have to do. The matrix generators, so there's a whole bunch in here. You'll see kind of weird things, random non-normal upper Hessenberg toplet 0 diag matrix.m. This is one of those kind of ad hoc ones I did for Rob. So there's code in here. It will split out a random non-normal upper Hessenberg toplets matrix with a 0 main diagonal. So these functions are really the only thing you need to write if you actually want to explore your own classes. All you have to do is write a function that just spits out a random matrix of whatever class you want. So I go back here. The examples folder, so this contains a whole bunch of examples. Example 1 has a ton of documentation. This is kind of just the most basic example, really explaining in detail what everything actually does. I'm just going to change this. So I'll just run that really quickly. It doesn't take long. So the breakdown is pretty much specify where you want to save things. So that's the working dir part. As it runs here, you can see starting parallel pool. So you do need that parallel processing package with Maple. If you don't have that, you can just go into the actual source code, search for par4, and just replace it with 4. Everything will work fine. This is the actual matrix generator. So random matrix, this is the -1, 0, 1, 5x5 case. So this will just, each time you call this, it'll generate a random -1, 0, 1, 5x5 matrix. And then generate random samples. That's, again, that's step 1. That's where you're computing your eigenvalues. Process data, step 2. Make your histogram. And then I have kind of a custom color map here. So those are the colors. That's kind of what that's their mapping. Sometimes it's useful to be able to customize that a little bit. And then spit out an actual image. So that's done. All right, so it created this folder with the working directory name there. It'll create the folder for you if it doesn't exist. Within the folder, again, it's broken down actually by the 3 steps. So data, this is just your raw data. They're always named, this is customizable as well, BHIME_1, 2, and so on, .mat. And it will always write a README. It's became very useful very quickly. I have a lot of old Bohemian Eigenvalue images that I don't know what they are, because this was not part of the package at the time. But it will tell you what you used when you called it, including some of the options that were used. And if you actually open this, here. So this file contains the eigenvalues there, so that's the 5 million length, a vector of length 5 million, and then just keeps a few other things around, just to make sure you actually know what the file contains. The process one, so this is your actual matrix, which is just your 2D histogram of counts at each bin. This one also gets README, just with some details there. The actual view over the image will just by default include all eigenvalues. So when you look at that bhime_1.mat file, it'll just make sure everything is included. And then the default size of the image, it has 1001 pixel height. It's an odd number because otherwise the real axis can get a little bit screwed up. So having an odd number is usually better. And if you jump to images, there's a README again. But that's what you get. So that's a random sample of 1 million of these matrices. Sometimes I get questions about the color map that I use. I used to get a lot of questions about kind of that 3 billion matrix example that I had on my third slide or so. Why did I color it all green and blue? I didn't. The color map was actually a rainbow. It's just the real axis eats up a lot of those colors. So as you can see here, the real axis eats up the blue into the green, into the yellow, orange, red, all the way into the white, which is the highest density. And then you're kind of just left with this bluish kind of color everywhere else. I'll show the second example. The second example on here, this is the exact same as the first example, but it shows some of the options that are available with the code in terms of customizing things a little bit.
So the desktop?
This? Oh, yes, it is. Thank you. So adding a margin there. So bottom is the imaginary, the lowest imaginary point. Top, left, and right. Num data files, so this is what you use if you want to compute more matrices, or the eigenvalues of more matrices than what you can store in memory. So in this case, I'm doing 5 data files. Each data file will contain the eigenvalues of 1 million matrices. By default, what does it do? By default, if you don't specify any of these options, I think it does 100, just do 100,000 matrices. I don't actually call it, but it will chunk things still if you don't actually specify numbers here, kind of at a low tolerance to ensure you're not going to end up with some kind of after letting it run for an hour, some sort of MATLAB error saying, hey, this matrix is too big to store in a file or something. Some other options on this one, so the margin is there. The height's 2001 pixels. Symmetry imaginary, so that's symmetry across the imaginary axis. You can do symmetry across the real axis, but that's guaranteed anyways because they're real matrices. The background color, so all ones, that's just white. And then everything's the same, so there's this option struct. You just pass it to each of the functions, and it will take care of integrating those as needed. So I'll just let that finish. While I'm waiting for that to finish. So on the actual GitHub page, there is descriptions of all the various options in here that you can use with the package in terms of all the various things you can play around with. Some things in here I don't use often. There is like this kind of max density, min density. On occasion, it doesn't happen often, but on occasion, I'll be generating an image where essentially the density will just be so high that you just get garbage. You can't see kind of that fine structure. So you'll chunk the images, maybe divide it into a 4x4 grid over some gigantic kind of pixels, gigantic DPI, I guess. That just allows you to ensure that the actual coloring lines up between those images. There's a few other things there. Some of these might not work, but all the things you would use in general should work, I hope. All right. So this one's going to look the same. The only difference is it has a white background. It's a little bit bigger. And it's 5 million matrices this time. So you get a little bit more detail. You can see kind of that diffraction pattern that we saw before around 0. And then kind of some of the other interesting patterns that are hidden in there. Kind of these star shapes around these eigenvalue exclusion zones. They all have eigenvalues at the center of them. I don't know. It doesn't show up there, but they are there. It doesn't show up because they're colored white. That's why it's not there. But the hope with this package is that it is easy to use, and if you have a class of matrices or a problem you're interested in, it's really easy for you to get up and running with it and just kind of jump into generating your own images. Okay, so why do we random sample? So Rob obviously showed this image, all 847 billion matrices. That's a lot to compute. For the most part, we use random sampling. It's very rare for us to actually look at all of these unless we know that there is, well, unless it's computationally feasible. Random sampling is fast. I mean, I can look at 1 million of these and get a pretty good idea of what the actual images of the Bohemian eigenvalues look like. So it gives us a pretty good idea of the distribution. It gives us the most probable eigenvalues, which has its disadvantages. So this is just a comparison. Again, 5x5 example, left-hand side, sample of 100 million. Takes about 10 minutes on a laptop. The right-hand side is all 847 billion matrices. You really don't lose that much information from a visual standpoint. From a computational standpoint, if you are looking at kind of some of the limits or max-min eigenvalues, you are going to lose some of that information. So this is just, again, some of the limitations. If you're trying to answer questions like how many distinct eigenvalues are there, I'll get to this shortly in terms of how I did that. How many real eigenvalues, highest density, it's usually 0. What are the smallest or largest eigenvalues? You're going to lose some of that information by random sampling. But you might be able to get good approximations or some idea of what value that might be approaching. We're also computing these eigenvalues numerically, so it's not pretty doing them symbolically. Wouldn't recommend it. There are some limitations there. So you do just get numeric approximations. If you ever zoom in on 0 in any of these images, you will see kind of noise around that, which is to be expected. But something like trying to count the number of distinct eigenvalues or the number of distinct, well, can't do character polynomials, but number of distinct eigenvalues, that's going to be a lot more difficult to do with numerics. It would be really interesting to see if anyone is able to do that for the 5x5 case. I'd be really interested if someone could get that 7.9 million number out of that data. Because I've always done it symbolically, just to make sure it is actually correct. Things like counting how many matrices of Rhapsody, inverting these matrices numerically, doesn't always work all that well. So there are some issues there where we then actually resort to symbolic computation. So before I jump into the second part, just have a few fun images. Rob showed this one as well. So this is the Upper Hessenberg with 0 main diagonal. That's the one Rob has a gigantic print of. This one's a fun one, so it's kind of weird looking. It's not an overly interesting class of matrices. This one I called border matrices. Essentially, first row, first column, last column of the matrix are filled with values. I think this is 15 by 15. And then they're just randomly filled with -1, 0, 1. There is no application or really meaning to these matrices that I know of. But why they're interesting is when I ran this, I ran into an error with the Eig function in Matlab. So I've computed probably over 1 trillion matrices, or eigenvalues of over 1 trillion matrices. And on rare occasions, Matlab actually fails at computing those eigenvalues for a real 15 by 15 matrix. Matlab version 2017 and earlier fails on this. Matlab version 2018 does not. There is nothing in the release notes that says what changed, which is unfortunate. There is another example with complex entries where we have, I think, as low as 12 by 12, where it will fail as well. And these are in fairly low height, so I think that one, so this has height 1. The imaginary one also has a height of 1, I believe. It gives you an error message saying algorithm did not converge. Yeah, so not very informative. I actually had to integrate kind of, in order to generate this image, because you keep getting these failures, and then the whole code, all the code fails, I had to put like a try-catch statement in there just to throw out those cases where it failed. I don't know if it's still in there. So I've been exploring that a little bit. I think on average it failed about 1 in every 100 million matrices. For this one, it's hard to actually catch them. There didn't seem to be any discrepancy between dimension. I think dimension 15 by 15 might be the smallest dimension where this one fails. For the complex one, 12 by 12 was the smallest dimension that we saw where we ran into issues. This one is not technically Bohemian, but it's a fun image anyways. So this is 3 by 3 matrices. The entries are sampled from a beta distribution. So they essentially have, so the parameters of the beta distribution is continuous distribution. And then it's actually scaled as well. Just guarantee numbers that are really high probability of being either 1 or -1, fairly low probability of being anywhere between. And you actually get all these algebraic curves kind of connecting the eigenvalues. So all the hotspots in the image, those are the 3 by 3 eigenvalues of -1, 1 matrices. And then the algebraic curves kind of appear out of that. And we can write down what those actual curves are. It's just a fun one. And the interesting thing, I don't have the plot here, but it is on the website. So I did do a little bit of work at one point. All this Matlab code worked for actually plotting the eigenvalue condition number as well. And the interesting thing is, as you follow some of these curves, you might be well conditioned along this curve, but poorly conditioned along this curve as you approach some of these eigenvalues. So there's some interesting properties behind this one. These ones, there's a few of these. These are not technically Bohemian either. I call these ones eigenfish because they tend to look like fish or sea creatures. They're essentially I don't know the exact matrix in this case, but probably a 3 by 3 matrix, and then let 2 of the entries in that matrix vary continuously between typically, maybe -5 and 5 or so. The rest of the matrix has height 1. They're just fun to look at for the most part. These are the ones where I'll generate maybe 1,000 of these at a time, go through them, pull out the fun looking ones, throw out the rest. I just enjoy making these ones. So you get all sorts of weird things happening in these. There's a few there. This one's a tri-diagonal matrix. I want to say 15 by 15. The entries are 1 plus I, 1 minus I, -1 plus I, and -1 minus I. That's on the gallery as well. Just some really interesting structures that appear in some of these. Don't have any idea why they appear, but they're fun to look at least. This is another tri-diagonal. So this is tri-diagonal entries sampled from -1 and 1. Again, a lot of just crazy detail happening in this image. I think that's maybe 16 by 16 in this case. And then back to this one. So this is, again, that random sample of 3 billion. So moving into how I actually did all 847 billion. So there were when we first looked at this image, there were obviously questions we had. How many eigenvalues are there? How many characteristic polynomials are there? What is the minimum eigenvalue? What is the size of this exclusion zone? Questions that we couldn't really answer just by looking at the eigenvalues directly. So that's just a sample of some of the questions we had at the time. So we needed a slightly different approach to actually analyze this problem. 847 billion matrices, that's a lot to do numerically. Brute force and Maple, just an estimation, would take about 25 years using unoptimized code, but gives you some idea of just how long this might take. There are symmetries that can actually be used to reduce the problem a little bit. Combining those symmetries can be difficult. Some of them are easy to use. Some are a little bit more difficult. Again, it'd be really interesting to see if someone could actually apply numeric approaches to do this, whether we can actually move away from the symbolics and do it numerically for things such as counting the eigenvalues. Although that might run into difficulties as the dimension grows. Some of the symmetries that we can use, so A and A transpose are both in the family of Bohemian matrices. We can throw out half of those. They have the same eigenvalues. A and negative A, again, can throw out half of those because we know what the eigenvalues are. The third one, this is a little bit more difficult. So if P is a permutation matrix, we could, so there's n factorial permutation matrices. We could reduce the class by at most n factorial, but we run into issues where identity matrix, simple example, any permutation of that is still the identity matrix. This one is difficult to do in practice. There are approaches. Daniel Lichtblau, one suggestion he had, so this was actually his idea, I believe. Is it his idea? Was it?
Wendy Mervold.
Wendy Mervold, make sure I give credit to the right people, was fix the order in which you fill the diagonal, and then when you do the permutations, that will be encompassed within that. So as long as you fix the order, so maybe -1s always come first on the diagonal, then 0s and 1s, you can at least capture some of this. Rhapsodic, again, for like the -1, 0, 1, 5 by 5 case, that's very difficult to actually do. You don't know if a matrix is rhapsodic or not. There's really no way to actually capture that. And I don't actually know what the reduction is there. Hoping to actually get that number in there eventually. So how I actually went about doing this for all 847 billion matrices. So they do have integer coefficients, -1, 0, 1. Hence the characters of polynomials. Also have integer coefficients. Very easy to parallelize, which is nice. We can do this in any compiled language just over the integers, which is going to just offer a substantial speed improvement over using something like Maple. I actually use code generation in Maple to generate the coefficients of the characteristic polynomials. Maybe not the best way to do it, but it worked. And then we can actually store in a hash table how often each of the characteristic polynomials actually occurs. And the actual, in terms of actually hashing that, so what I did, so you could just do so I did this in C++, you could do, I think you can use an unordered map or something like that, and actually have the index, I believe, as an array. You can do better than that. So this is an example of a characteristic polynomial, and then you can actually encode that as an unsigned 64-bit integer. This works for the 5 by 5 case. This kind of method would not work for the 6 by 6 case, because this requires that the maximum height is less than 128, less than 128. But essentially, you start off, you remove that x to the 5th term. It's redundant. It's in all the polynomials. And then you take the coefficients mod 256, just get rid of any negatives. And then you evaluate the resulting polynomial at 256. And that's then unique over all characteristic polynomials in that class. The max height in this class is about 80. Before I ran this, I kind of just ran, I don't know, 10 million matrices, got some idea what the max height was at, and then kind of hoped it would work. Put a check in there to make sure it didn't actually go above 80. And just by repeatedly doing quotient remainder computation, you can actually recover the characteristic polynomial from that. So this is how I went about doing all 847 million matrices. The code I used actually I don't believe it's available yet. I will get that on GitHub soon. So as I said, I use C++. Took about 62 hours on my laptop to do this. That's not using parallel code. That's just serial code. You can easily improve this by parallelizing that, which I did at one point in time, which is pretty substantial improvement over what Maple could do. And there are pretty obvious improvements in that C++ code that could be made. But for the purpose of what I was doing, I just wanted to get the job done. You could probably reduce this pretty substantially, but it worked. Worked for what I was doing. So this allowed us to really recover some of these results for these classes of matrices. So for the -1, 0, 1 case, we were able to get the number of characteristic polynomials up to the 5 by 5 case. We do not know for the 6 by 6 case what it is, as Rob kind of discussed. We can also plot all the eigenvalues. That's how this image of all of those 847 billion matrices was generated. Is you have your characteristic polynomials, you know the frequency of each of those. It doesn't take long for Matlab to compute the roots of 1.8 million degree 5 polynomials, so you can pretty quickly recover that image. And the next thing we wanted to do was actually count the eigenvalues. So we were curious how many points actually belong to this image. So we have all 1.8 million degree 5 characteristic polynomials. We can count the eigenvalues pretty easily. This is the approach that I took. Before I took this approach, so I was kind of thinking, okay, how should I count the eigenvalues, or the number of roots of this set of polynomials? So I was being creative using GCDs and trying to generate like a GCD-free basis and all this crazy stuff. Wrote some stuff, let it run, took about a month. Was happy, got the answer back. But then I tried just for fun this factors function within Maple. It got the job done in about 2 hours versus my 1 month. So I was pretty impressed with that. That's what I use now. I don't use the custom code that I wrote for the job. You call the factors, and it's going to whatever it returns, there's going to be pairized GCDs 1, and you can verify that, and then you just sum the degrees, and you get your answer back. So factors will return an actual list of polynomials. Before you do that, you make all the input characteristic polynomials square free. The other thing we wanted to do is count the number of real roots. So after getting this list of all the factors, we actually used this real root counting function. So my PhD co-supervisor, Mark Moreno-Mazza, he has done a lot of work on this regular chains package in Maple. And there's a lot of functionality there in terms of counting real roots, isolating them, other functionality there. And takes maybe half hour, 45 minutes to run over that list that's returned from factors to actually give you an exact number back, which is pretty impressive for the number of polynomials you're actually looking at. When we throw all the numbers together, so there's OEIS sequences up there. If you happen to get the 6x6 case, let me know. So it's about 8 million eigenvalues in total, but about a third of those are real. So that is kind of that really high density on the real axis. And that leads us just kind of where to go from here. So what other questions do I want to look at? What other things do I want to answer? One thing I started to look at a little bit, kind of relating to one of my other research projects, is how large is the set of Jordan canonical forms? So you have your set, you have all 847 billion matrices. If you compute the Jordan canonical form of those, throw them into a set, how many different Jordan canonical forms are there? Not sure how I'm going to approach that yet. Why is there this diffraction pattern around 0 that we see? We have some ideas why it's there, although it's difficult to kind of quantify what causes it. It's to do with the fact that all the eigenvalues are algebraic numbers with minimal polynomials of maximum degree 5. Something to do with that. Try and quantify that. And then for the 5x5 case, just counting how many matrices of Rhapsody, you can do that from the characteristic polynomials, which is kind of nice. So hopefully I'll get that done over the next few days. So that's